Recognizing patterns. One of the most helpful strategies for both code optimization and algorithm development in general is to find patterns within the problem at hand. Often, the discovery of a pattern can help you cut through all the complexity of a problem and develop an algorithm that is actually quite simple. Here's a great example. There is a game I call the coin game in which two players compete in the following way. They start with a pile of coins and each player has the choice of removing either one or two coins from the pile. The player who removes the last coin loses. Fun, right? It turns out that this isn't a game of a random chance, and with the right strategy, you can force your opponent to take the last coin and lose the game. If there's just one coin in the pile, the player whose turn it is loses, since they have no choice but to take the last coin. If there are two coins left, the player whose turn it is can force a win. This is because they can take just one coin and thereby force their opponent to take the final coin. When there are three coins remaining, the player whose turn it is can force a win since they can remove two coins, forcing their opponent to take the final coin. Now, when there are four coins left, the current player is in trouble. If they remove one coin, the opponent is given a pile of three coins, which we established earlier can allow that player to force a win. Similarly, if the current player removes two coins, the opponent is left with two coins, which can also allow the opponent to force a win. If we were to write a function that calculated whether you can win the game when presented with a coin pile of a given space, what approach should we take? If we think about this carefully, we realize that we can use sub-problems to help calculate an accurate result. If any number of coins, in any number of coins, this would make top-down recursion a natural fit for solving this problem. Here's a Ruby implementation of a recursive approach. So we define game underscore winner with an argument number underscore of underscore coins, comma, another argument current underscore player equal quote u. So if number of coins is less than or equal to 0, return current underscore player. End. And then we create the next player algorithm. If current player equals to u, next player equals to them. Else if current player equals to them, next player equals u, and then end. Then we use a recursive function. If game winner with an argument number of coins minus 1, next player equals to current player, or game winner argument number of coins minus 2, next player equal current player, return current player, else return next player, and end. So what does this code means? This game winner function is given a number of coins and the player whose turn it is, either you or them. The function then returns either you or them as the winner of the game. When the function is first called, the current underscore player is you. We define our base case as when the current underscore player is dealt 0 or fewer coins. So less than or equals to 0 are our base case. This means that the other player took the last coin and the current player by default won the game. So it means that the current player took the last coin, therefore the current player by default won the game. We then define a next player variable, which is in this case the if-else if, which keep track of which player will go next in this algorithm. Then we do our recursion. We recursively call our game underscore winner function on piles of coins that are both 1 and 2 coins smaller than the current pile. Again, we do our recursion. We recursively call our game underscore winner function on piles of coins that are both 1 and 2 coins. So piles of coins that are both 1 here and 2 coins. Smaller than the current pile. So number of coins minus 1 or number of coins minus 2. And see if the next player would win or lose in those scenarios. If the next player loses in both scenarios, that means the current player win. So again, and we see if the next player would win or lose in those scenarios. If next underscore player loses in both scenarios, that means the current underscore player will win. If in this if statement, this or of if statement, like the game winner with number underscore of coins minus 1 lost by the next player, or the next player loses that did not meet those conditions, that means the current player will win. This isn't an easy algorithm, but we pulled it off. So it's kind of like the recursive function on this sub problem, kind of like the factorial we have tackled in the previous video, but we pulled it off. Now let's see if we can optimize it. Now we can improve this by using the memoization technique you learned about in dynamic programming, which could bring the speed up to O(n), with n being the number of coins in the starting pile. So currently, this recursion has an O(n) squared because it's a recursion. That's a huge improvement if we could bring it to O(n). Because n is just a single number, I could conceive that we can make an algorithm that takes just O(1) time, since we don't actually have to touch n items in an array or anything like that. If someone told me they figured out an algorithm for the coin game that was just O(1), I'd believe them. So let's try for O(1). So currently it's O(n), but we can use a dynamic programming that could bring it to O(n). However, we could conceive much better like an algorithm that takes just O(1) times. So since we don't actually have to touch n items in an array or anything like that, a better goal would be an O(1) algorithm or O(1) speed. So while each problem has a unique pattern, I found a technique for finding patterns that help across all problems, and that is to generate numerous examples. This means we should take a whole bunch of example inputs, calculate their respective outputs, and see if we can detect a pattern. So if we map out who wins for coin piles of size 1 through 10, we get this table: number of coins, then winner. So 1, them, 2, 3. So there's a pattern. The pattern becomes clear once we lay it out in this way, and it's easier to grasp the pattern if we represent it in this way. So I would recommend you find other ways to represent your idea or algorithm, such as this. It really depends on how what is more intuitive based on your experience. Now the pattern becomes clear when we lay it out this way. Basically, starting with 1 coin, every number gives victory to the opponent. Otherwise, you are the winner. So if we take the number of coins and subtract 1, each them ends up at a number that is divisible by 3. At this point, then, we can determine who will win based on a single division calculation. So here, it's a much shorter algorithm. We define game underscore winner with only one parameter, number underscore of coins. If number underscore of coins minus 1 divided by is divisible by 3 equals to 0, or divided by 3 equals to 0, return them. Else, return you. And end. So it's a simple if-else statement. So this code is saying that notice that we didn't use recursive function. We use a simple if-else statement. This code is saying that if after subtracting 1, the number underscore of underscore in coins is divisible by 3, the winner is them. Otherwise, you are the winner. Because this algorithm consists of a single mathematical operation, it's O1 in both time and space, and it's also a lot simpler. So this is a real win-win. So this is how we are able to use pattern to make the memory, unit of memory in steps in O1 time, coming from an O(n) squared implementation. Here's an example, another example, where we can use pattern recognition and magical lookups together to optimize an algorithm. So remember the previous video, we discussed how lookups can use to make our code easier, and it's the natural way to do because the fastest algorithm is O1. So here we will combine pattern recognition and magical lookups to optimize the algorithm. The next problem, known as the sum swap problem, it goes like this. We want to write a function that accepts two arrays of integers. As an example, let's say our arrays array underscore 1 equals to 5, 3, 2, 9, 1, sum 20, and then array 2 is equals to 1, 12, 5. So as you can see, we have sum 18. Currently, the numbers array 1 add up to 20, while the arrays while the numbers in array 2 add up to 18. Our function needs to find one number from each array that can be swapped to cause the two array sums to be equal. So we can swap this 2 and 1 so that it's the sum is equals to 19. In this example, if we swap the 2 from the array 1 and the 1 from array 2, we'd get that. To keep things simple, our function won't actually perform the swap, but will return the two indexes that we'd have to swap. So in order for us to make this function, we'll actually make it simple by returning the two indexes that we want to swap, like this 0, 1, 2, 2 index, and this 0 index on our function. So we can do this as an array containing the two indexes. So in this case, we swap index 2 of array 1 with index 0 of array 2. So we'll return an array of 2, 0. In a case where there is no possible swap that makes the two arrays equal, we'll return nil, so null, if we can't swap a number that would make this sum of two array equal. One way we can write this algorithm is to use nested loops. That is, our outer loop points to each number from array 1, an inner loop can iterate over each number from array 2 and test the sums of each array if we were to swap the two numbers. So that's the one way to do that. But because our nested loop approach visits m numbers from the second array for each of the n numbers of the first array, this algorithm is O(n) times n. So I'm discussing n and m because the arrays may be two different sizes like this. It would seem that we absolutely have to visit each number from the two arrays at least once. So in order for us to imagine the best imaginable scenario, it would seem that the array would visit at the elements or index at least once, since we need to be aware of what all the numbers are. But it's possible that this may be all we need to do. If so, this would be O(n) plus m. So the best imaginable speed that we can think of is O(n) plus m to calculate this. Next, we need to try to dig up any patterns hidden within the problem. Again, we're using pattern to create our function. So we're gonna use this kind of representation to find a pattern or dig a pattern that will allow us to understand it and be able to write the function. So again, the best technique to dig up pattern is to come up with numerous examples and look for patterns among them. So let's look at a number of different examples where swapping numbers will cause the two arrays to have equal sums. So as you can see, after swap, you have 15, 15, then 18, 18, then 5, 10. We swap 5, 10, you have 40. So we have three patterns that emerge here. One pattern is that to achieve equal sums, the larger array needs to trade a larger number with a smaller number from the smaller array. So the larger array needs to trade a larger number with a smaller number from the smaller array. So that's first pattern. A second pattern is that with a single swap, each array changes by the same amount. So a single swap, each array will change by the same amount. For example, when we swap a 7 with a 4, one's array sum decreases by 3, while the other array sum increases by 3. A third interesting pattern is that swaps always cause the two array sums to fall out exactly in the middle of where the two arrays began. In this case, for example, array 1 was 18 and array 2 was 12. When making a correct swap, the two arrays land at 15, which is their middle, which is exactly in the middle of 18 and 12. When we think about it further, this pattern is a logical outgrowth of the other pattern, since a swap causes the two arrays to shift their sums by the same amount. The only way to make their sums equal is to meet in the middle. Based on this, if we know the sums of the two arrays, we should be able to look at any number in one of the array and calculate what number it should be swapped with. So let's take this sample again, 18, 12. So let's look at different numbers from array 1 and figure out what number we'd swap it with. We can call this other number its counterpart. So we need the counterpart is the one we figure out that we want to swap it with. So like for example, this array 1, we want to know what is the number we want to swap it with in array 2. So that's the counterpart. Let's start with the first number from array 1, which is the number 5. What number would we want to swap the 5 with? Well, we know that we want array 1 to decrease by 3 and array 2 to increase by 3. So we need to swap the 5 with the number 2. It's just so happened that array 2 doesn't contain a 2, so the 5 cannot be successfully swapped with any number from array 2. If we look at the next number from array 1, it's a 3. We'd have to swap with the 0 from array 2 to get the two sums to be equal. However, there's no 0 in array 2. And the last number from array 1, though, is a 7, since you have 2, 3. We can calculate that we'd want to swap the 7 with a 4 to make the sum both land at 15. Luckily, array 2 does contain a 4, so we make a successful swap. So this is, as you notice, we mentally imagine this first, or we wrote it like this. The cases that might be possible, or the possible cases in this representation before we write it in code. So how do we express this pattern in code? Well, we can first determine how much an array sum needs to shift using this calculation. Here, sum 1 is the sum of array 1 and sum 2 is the sum of array 2. So we need to calculate the sum first. If sum 1 is 18 and sum 2 is 12, we'd end up with a difference of 6. We then divide that by 2 to determine how much each array needs to shift. This is the shift amount. So this is the formula for shift amount. Sum 1 minus sum 2 over 2. So we can start assuming that the sum 1, of course, is greater than the sum 2. So we can start building our algorithm by first calculating the sums of the two arrays. We can then loop through all the numbers in one of the arrays and look for the counterpart in the other. So we need to calculate first, and then we need to look at each index of the first array, or the sum 1, then look for the counterpart in array 2. If we were to iterate over each number in array 2, for example, we know that the current number would have to be swapped with its counterpart. So again, if we were to iterate over each number in array 2, for example, we know that the current number would have to be swapped with its counterpart. So again, if we were to iterate over each number in array 2, for example, we know that the current number would have to be swapped with its counterpart in that index in array 2, which would be the current number plus the ship amount. So the current number in the array 1 plus the ship amount. For example, if the current number is 4, to find its counterpart, we add the ship number to it 3 and get 7. Therefore, we look 7 if the array index 2 value is 7. This means we need to find a 7 in array 1 to find a swap with our current number. So we'd figure out that we can look at any number in either array and know exactly what its counterpart from other array should be. So again, we figure out that we can look at any number in either array and know exactly what its counterpart from this formula that we created. But how does this help? Don't we still need to use nested loops and an algorithm that is O n times n? That is, for each number in one array, we have to search the entire array for the counterpart. Indeed, if we could find a number's counterpart from the other array in just O one time, if we could find a number's counterpart from the other array in just O one time, our algorithm would be much faster, and we can achieve those quick lookups by following the usual technique of bringing our good old friend hash table. So if we could find the array 2, that we're looking the counterpart with in O1 time, we could bring that into an O1 speed. So I accidentally make it larger. So if we store the numbers from one array in a hash table, we can then immediately find any number from it in O1 time as we iterate through the other arrays. Here's the complete code. So again, if we store the numbers from one array in a hash table, we can then immediately find any number from it in O1 time as we iterate through the other array. So here's the complete code using a hash table, and the other is array. So here, depth sum swap array 1 array 2, then hash table equals empty, sum numbers 1 equals to 0 initially, sum number 2 equals 0 initially. Then gets sum of first array while storing its value in a hash table together with an index. So we get the value of the first array while storing it in a hash table using this each do code. So array underscore 1 that each underscore with underscore index do argument num comma index sum underscore 1 plus equals num, so it means to iterate on each index, and then hash table num equals to index. So we have a key or hash table with an argument num, which is the key, and a value index, and we end it. And then get sum of second array underscore 2 that each do argument only num. So instead of adding it to hash table, we just have an argument num, and then sum underscore 2 plus equals to num end, so which to get sum of all the second array. So that plus equals are actually to get the sum. So calculate how much a number in the second array needs to ship by. So ship amount equals to sum 1 minus sum 2 over 2. So this is the ship amount. Iterate over each number in second array. Then we iterate again over each number in the second array. So array underscore 2 that each with underscore index do. Now it has an argument num comma index, 2 arguments, just like array 1 earlier. Then check hash table for the number's counterpart in the first array, which is calculated as the current number plus the amount it has to shift by. If hash table num plus ship amount, return hash underscore table num plus ship amount, comma, index. So again, this is the code. It's an if else. So if hash table num plus ship amount, return hash underscore table num plus ship amount, comma, index. So it means that if it's equal, this array2 equals to that num plus ship amount, we return that hash table num plus ship amount and the index n. And so and the last code, return nil. So if we didn't find that, we return nil or null. This approach is much faster than original on times m1. So if we consider array1 to be n and array2 to be m, we could say that this algorithm runs in on plus m time. So even though we use hash table, we still have this on plus m time complexity. Well, we do iterate over array2 twice, and it's technically 2m. It becomes m since we drop the constant. So one of the things is that this hash table does not always makes your time complexity O1. It can bring down from n times n to n plus m. So this approach takes an extra on space since we copy all numbers from array1 into the hash table. So there's it's an on plus m and then additional on space, but it will be 2n. But since we drop the constants, it's considered an n plus m algorithm. So greedy algorithm, this may sound like a strange term, but here's what it means. A greedy algorithm is one that in each step chooses what appears to be the best option at that moment in time. This will make sense with a basic example. Let's write an algorithm that finds the greatest number in an array. One way we can do this is to use nested loops and check each number against its every other number in the array. So to find the greatest number, or to write an algorithm that finds the greatest number, one way to do this is to use nested loop and check each number against other number in the array to find what's the greatest. When we find the number that is greater than every other number, it means we found the greatest number in the array. As is typical for such algorithm, this approach takes on squared time. So when we find the number that is greater than every other number, it means we've found the greatest number. As typical for this, it's on squared because we need to compare it. So we use nested loops and check each number against every other number in the array. So another approach would be to sort the array in ascending order and return the final value from the array. If we use a fast sorting algorithm like quicksort, this would take on log n time. So to find the greatest number against these arrays, it would take n log n time if you sort it first. There's a third option, which is the greedy algorithm. Here it is. We define max with an argument array, greatest underscore number equals array argument 0. So initially it's 0 or the index 0. So we assume that the greatest number. Then we use an each do loop. Array that each do with an argument number. If number is greater than greatest underscore number equals the number. And then after that, we created that each do if loop. We end, and then the last line of code, return greatest number, and then end this function. So as you can see, the first line of our functions assume that the first number in the array is the greatest underscore number. Now, this is a greedy assumption. That is where declaring the first number to be the greatest underscore number because it's the greatest number we've encountered so far. Of course, it's also the only number we've encountered so far, But that's what greedy algorithm does. It chooses what appears to be the best option based on the information available at that moment in time. So that's actually smart because we assume the first index to be the greatest and then change it as we iterate. Next, we iterate over all the numbers in the array. As we find any number that is greater than the greatest underscore number, we make this new number the greatest number. Here, too, we're being greedy. Each step selects the best option based on what we know at that moment in time. Kind of like in Gcash algorithm, which we will discuss in the next videos. Basically, it compares the currently least path or the currently greatest or least value depending on what you're calculating. And while being greedy isn't a virtue in a societal context, it can do wonders for algorithm speed. So, and while being greedy isn't a virtue in a societal context, it isn't a virtue in a societal context, it can do wonders for algorithm speed. So this algorithm just takes O(n) time as we touch each number in the array just once. So remember, n log n is much slower than O(n) time. So this each do loop or the greedy assumption makes our algorithm takes O(n) time. So here, another example, largest subsection sum means to write a function that accepts an array of numbers and returns the largest number that could be computed from any subsection of the array. So here's what I mean. So let's take, so basically largest section means to write a function that accepts an array of numbers and returns the largest sum that could be computed from any subsection of the array. So here's what I mean. Let's take the following array: 3, -4, 4, -3, 5, -9. If we compute the sum of all numbers in the array, we'd get -4. But we can also compute the sum of subsection of the array like this: 3, 2, and -7 from the first part, middle, and last part. When I refer to subsection, I mean contiguous subsection in the array, not the node like separation of data. This subsection is a section of the array that contains a series of numbers in a row. The following is not a contiguous subsection since the numbers are not in a row. Like a node, this number is not what we're talking about here. So our job is to find the largest number, largest sum that can be computed from any subsection within the array. If, for example, the largest sum is 6 derived from the following subsection, so to make the discussion simpler, let's assume the array contains at least one positive number. Now, how can we write the code to calculate the largest subsection sum? So again, to make the discussion simpler, let's assume the array contains at least one positive number. So now how can we write a code or function to calculate the largest subsection sum in an array? So that's another issue. One approach would be to calculate the sum of every subsection within the array and pick out the greatest one. So again, one approach would be to calculate the sum of every subsection within the array and pick the greatest one. However, there are about n squared over 2 subscription for n items in an array, subsections for n items in an array. So the mere generation of different subsections would take O(n) squared time. So again, however, there are about n squared over 2 subsections for n items in an array. So just the subsection would take you n squared over 2. So the mere generation of different subsection would take O(n) squared time. So at first glance, O(n) speed or O(n) time seems beyond our reach. So how can we add multiple subsections? By iterating over the array a single time. So how can we add multiple subsection by iterating over the array a single time. A greedy algorithm in this context would attempt to grab the greatest sum at each step as we iterate over the array. So a greedy context here would be to attempt to grab the greatest sum at each step as we iterate over the array. Here's what this might look like as we iterate over the earlier example array. Starting at the front of the array, we encounter a 3. In a perfect greedy fashion, we'll say that our 3 or our greatest sum is 3. So we assume the 3 first. Next, we can add this to the previous number of 3. We can get a current sum, -1. So 3 is still our greatest sum. And then we hit the 4. We add this to our current sum. We get 3 as of now. As of now, 3 is still our greatest sum. The next number, we reach -3. This puts our current sum at 0. Well, 0 is our current sum. 3 is still our greatest sum. So while the current sum we calculate is 0, our greatest sum is still 3. Next, we reach the 5. This makes our current sum 5. In our grid, we'll declare this to be the greatest sum, as it's the greatest sum we've encountered so far. So we change the 3 to 5. We then reach the last number, which is -9. This deflates our current number to -4. By the time we get to the end of the array, our greatest sum is 5. So if we follow this pure grid approach, it would appear that our algorithm returned 5. However, 5 is actually not the greatest subsection sum. There is a subsection in the array that yields a sum of 6. The problem with our algorithm is that we only calculated the largest sum based on subsections that always begin with the first number in the array. But there are other subsections that begin with numbers later on in the array, such as this 4, -3, and 5, which start at not at index 0 but at index 2. And we haven't accounted for those. Our greedy algorithm then didn't pan out as we'd hoped. But we shouldn't give up yet. Often we need to tweak greedy algorithm a bit to get them to work. So the next step, let's see if finding a pattern may help. It usually does. As we've seen before, the best way to find a pattern is to generate lots of examples. So let's come up with some examples of arrays with their largest subsection sums and see if we discover anything interesting. So you can see here we have 5, then 6, then 3, and then 5. When analyzing these cases, an interesting question emerges. Why is it that in some cases the greatest sum comes from a subsection that starts at the beginning of the array, and in other cases it doesn't? So why is it that in some cases the greatest sum comes from a subsection that starts at the beginning of the array, and in other cases it doesn't? In looking at these cases, we can see that when the greatest subsection doesn't start at the beginning, it's because a negative number broke the streak. So because a negative number broke the streak, that is, the greatest subsection would have been derived from the beginning of the array, but a negative number killed the streak, and the greatest subsection has to start later on in the array. Like here, the 1, 1, 0, -3, 5. So we have 5 at the end. So it breaks that. And then another negative number, 2, -3, 1, 2, -1. But wait a second. In some cases, the greatest subsection includes a negative number, and the negative number didn't break the streak. So in some cases, the greatest subsection includes a negative number, and the negative number didn't break the streak. So what's really the truth? So what's the difference? The pattern is, if the negative number causes the preceding subsection sum to sync to a negative number, the streak is broken. But if the negative number simply lowers the current subsection sum and the sum remains a positive number, the streak isn't broken. So if the sum is not negative, it's still positive. The streak isn't broken. If you think about this, it makes sense. If we're iterating through the array, our current subsection sum becomes less than 0. We're best off just resetting the current sum to 0. So, if we're iterating an array and our current subsection sum becomes less than 0, we're best off resetting the current sum to 0. Otherwise, the current negative sum will just detract from the greatest sum we're trying to find. So otherwise, the current negative sum will just detract from the greatest sum we're trying to find. So let's use this insight to tweak our algorithm. Again, let's start with the 3. The greatest sum is currently 3. So 3, negative 4, 4, negative 3, 5, negative 9. So first, the greatest sum is 3. Next, we encounter the negative 4. This would make the current sum negative 1. So since we're trying to find the subsection with the greatest sum and our current sum is negative number, we need to reset the current sum to 0 before continuing on to the next number. So again, it becomes negative. That's why we need to reset. So until it's not yet positive, we have to reset. If it's a negative, we have to reset. We also start a brand new subsection beginning with the next number. Again, the reasoning is that if the next number is positive, we may as well just start the next subsection from there without letting the current negative number drag down the sum. Instead, we're going to perform a reset by resetting the current sum to 0 and considering the next number to be the beginning of a new subsection. I think that's pretty smart reasoning. So let's continue. We now reach a 4. Again, this is the beginning of a new subsection. So the current sum is 4, which also becomes the greatest sum we've seen so far. Next, we encounter the negative 3. The sum is now 1. We next come upon a 5. This makes the current sum 6, which is the greatest sum as well. Finally, we reach negative 9. This would make the current sum negative 4, in which case we reset it to 0. However, we've also reached the end of the array and we can conclude the greatest sum is 6, and indeed, that is the correct result. So here's the code for this approach. So def max sum with one argument array, current sum underscore sum equals to 0, greatest underscore sum equals 0. And then we use an each do if else statement here. Array.each do with an argument num. If current sum is a negative number, reset current sum to 0. So if current underscore sum num is less than 0, current underscore sum equals to 0. Else current underscore sum plus equals num. It means we move to the next index. Greedily assume. So else current underscore sum go to the next index, and then greedily assume the current sum is the greatest sum. If it's the greatest sum, and we've encountered so far, greatest sum equals current sum if current sum is greater than the current greatest sum, which will start with 0, and then end, and then the last code return greatest underscore sum. So this kind of code, the last part, kind of like mimic the greatest sum, which is assuming the greatest sum to be the first index. Using this greedy algorithm, we were able to solve this thorny problem in just O time, as we look through the array of numbers just once. That's a great improvement over our initial O(n)² approach. So from O(n)², we are able to make this in O time by using a greedy algorithm. In terms of space, this algorithm is O1 as we don't generate any extra data, which is a huge bonus. While the discovery of a pattern helped us discover the precise solution, by adopting the greedy mindset, we knew what kind of patterns we were looking for in the first place.